So we are looking at quantitative assessment of air risk. And again, we're pushing off some of the work that has been done before. I don't think we are reinventing the wheel here. So some of these works like this one and this one, you may also have seen in the ground risk set of slides. Well, that's because they address both ground and air risk, unsurprisingly, as we know, both SORA and the quantitative risk assessment methods address separately the ground risk from air risk. It makes sense. But there are also a few papers, few works that specifically address the air risk, and they all more or less have the same kind of methodology. So what is it about? So we look at the flights in the vicinity of an airport or of a city. And here on the graph, I'm showing the trajectories that flew in to Stockholm Arlanda Airport. So these orange things are the ADS-B trajectories taken from open sky. And while these blue ones are the potential so-called CDOs, continuous descent operations. They're not always in use, but anyway, those are the kind of ideal trajectories. We can also look at what happens if the aircraft use these better trajectories. And we may also concentrate in a certain altitude band and understand what airspace is available within this altitude band for the UTM, UAM operations. And we are particularly in this set of slides, I will also be looking at flights from a certain hospital, imagining some kind of emergency medical services operations for UAM. Maybe we'll speak more about applications of UAM, UTM later, but here we're assuming this one. And now the processing. How do we process the flight data? So we have a certain region of interest, ROI, and it's pixelated. It has pixels. And here is, let's say, 1 pixel in this region of interest. And we look at the trajectories of all aircraft that fly through the pixel. So these blue things, okay? So we look at the trajectories that fly through the pixel or within certain distance, like 300 meters from the pixels, from this pixel, because these are the aircraft that potentially impact the drone operations within this pixel. And 300 meters is, you know, the certain CNS, communication, navigation, surveillance requirements and errors. So we don't really know exactly where each aircraft is and where each drone is. So this certain radius around the flying object, protected airspace zone, or whatever you call it, is always assumed that, well, we don't know exactly where the vehicle is. So anyway, we are looking at this pixel and at all the aircraft that flew through this pixel within a certain time horizon, 12, 24 hours, 16 hours, whatever makes sense. And one thing we are interested in is the expected number of aircraft per unit time, or if you want, the air traffic intensity in this pixel. And the average intensity over this time horizon is just the number of aircraft that pass through the pixel divided by the time horizon, right? So if you had 12 aircraft that passed through the pixel within 12 hours, then essentially traffic intensity is 1 aircraft per hour on average. Of course, you can also do more fine-grained analysis, looking at different times of the days or even specific hours. But on average, within these 12 hours of operations, whatever this time horizon is, you have some kind of average traffic intensity or expected number of aircraft per unit time. Okay, so that was about the aircraft. And now we look at our drone or UAM vehicle, whatever it is. So this, maybe this is red thing is the path or part of the path of the drone. And we say that this small t is the time for our drone to go through the pixel. And we assume that it doesn't depend on the pixel, that all the pixels are passed during the same time. So the drone spends the same time in every pixel. But again, if you want, you can do this fine-grained analysis with different speed profiles and how much of the pixel, does it only clip the corner or goes all the way across the pixel. Anyway, for simplicity, again, going in the pixelated or grid domain, we assume the drone goes from pixel to pixel, spending a certain time, the same amount of time in each pixel. And then, okay, we have the traffic intensity. So this is the number of aircraft in the pixel per unit time. And small t is how much our drone spends in the pixel. So the expected number of conflicts with aircraft in this pixel is just this multiplied by this, right? So there is the average traffic intensity, or the number of aircraft that pass through the pixel per unit time. And this is how much time you spend in a pixel. So of course, the expected number of aircraft that you're going to see or conflict with in a pixel is the intensity multiplied by the time you spent. And it kind of makes sense if you assume that, you know, these aircraft are the cars and you're trying to cross the highway full of cars, then you may want to run and spend less time on the highway to minimize your probability of being hit or expected number of cars that hit you. Anyway, again, there is nothing too complicated with this formula, simple multiplications and divisions. And here is what we see from the data, something you may call the air risk map. So underneath there is Stockholm. You don't see it yet, but you will see in other pictures where we will have less flights. And these blue and red are the pixels colored with different colors, blue and red, which show the expected number of conflicts with aircraft at different places. So like over here, where there is no blue, no red, there are no conflicts. Where there is blue, there is certain number of conflicts, and where there is red, then we have much more. So that's the occupancy of pixels over time, over 16 hours. You can also look at the fleet types in Arlanda, and well, more or less they are standard fleet types. We don't know what is the load factor, how many people there are in the aircraft, but well, you can assume that it's something standard. And you can calculate now, again, we are calculating the expected fatality rate expected from the conflicts with the manned aviation, trying to reach, again, this equivalent level of safety with the manned aviation, which should probably be the goal of the risk assessment, or at least of quantitative risk assessment. Anyway, if we know the expected number of conflicts of aircraft with aircraft in every pixel, then if your drone goes along a certain path P, then you summing up the expected number of conflicts over all pixels in P, and that gives you the expected number of conflicts along a path. Okay, so I'll try to draw pixels, but anyway, so maybe these are pixels, and your drone goes like this through the pixels, and in this pixel it has certain expected number of conflicts here, expected number of conflicts here, and so on. So over the whole path, the expected number of conflicts is of course the sum over all pixels through which the drone passes. Okay, so that's the expected number of conflicts in a path. Now, how long does it take the drone to fly the path? Remember that we are interested in the expected fatality rate, so not just how many conflicts and hence fatalities you may have in the path, but also how many fatalities you have per flight hour. So it's expected fatality rate, not just the expected fatality. Now, the time to fly the path P is just the number of pixels in the path times what you spend in the pixel. So remember, the small t is how long it takes for the drone to pass through a single pixel. And then finally, the expected conflict rate for the whole path is, well, this thing, the expected number of conflicts, divided by the time it takes to fly P. So you take this thing, the expected number of conflicts, here it is, and divide by the time to fly P, which is this. So here is the formula. And interestingly, since this t comes both in the numerator and the denominator, it cancels out. So no matter how long it takes you to go through a pixel, the conflict rate is this. It's essentially the average occupancy of the pixels along your path. Okay, so you can do the arithmetic. This capital T is the time horizon, and you can take it out of the sum, and then in the sum you just have the summation of the occupancy rates over all pixels and divide by the number of pixels. So the expected conflict rate is the average occupancy divided by the time horizon. So that's how often you conflict with aircraft. Now, in SORA and also in other EASA documents, they say that essentially, if you collide, if you have a conflict, you collide, and everybody dies in the aircraft with which you have collided. So if you want to calculate the expected fatality rate, you have to multiply the conflict rate by the number of passengers. And again, looking at the fleet type and also at some of the prior work, well, we multiply this by 180. That's the average or assumed number of people in an aircraft. So here is the formula for the expected fatality rate. Again, we can also do this fine-grained analysis only and trying to understand how many passengers are around every particular aircraft and so on. But for a crude estimation, this is good. So that's the expected fatality rate. And well, here is your mission risk map, if you will. So assume that this is the hospital from where you're starting out to fly. And then depending on where you fly, you have different fatality rates. And essentially what it shows, so never mind the scale here, you know that the expected fatality rate should be kept below 10 into -6, or 1 fatality per million flight hours. Well, and here you have numbers like 20, 40, and 100, and so on. So essentially, you can fly here. That's okay, because you don't intersect any aircraft path. You can fly up to here, but as soon as you intersect an aircraft path, your fatality rate skyrockets. You don't want to fly through there. More or less, you have to stay away from the places in the airspace where conventional aviation flies. So in this sense, the mission risk map is boring. It's really a 0-1 or black and white map. I mean, do fly here, do not fly here. And there is this quite clear boundary between the no-fly zones and the zones where it's safe to fly from the point of view of the air risk, from the quantitative assessment of air risk. Okay, so that's the map, and maybe now you can try to see that underneath here we do have Stockholm, so maybe you recognize some of Stockholm features. Interestingly, if you take Bromma out of the picture, then the mission risk map looks much, much better. All of a sudden you can fly to many more places in Stockholm, than if Bromma traffic were taken into account. So you can basically fly everywhere except to the north, where north of Stockholm you have Arlanda. It more or less shows that an unsurprising fact that having an airport in the city center is nice, or close to city center is nice, as Bromma does. Bromma is close, but of course it creates a lot of traffic over the city center, and that airspace becomes unavailable for UAM. I mean, I know that this hot topic of whether Bromma should be there or should not be there, and well, from the UAM point of view, the 2 cents is that, well, if you remove Bromma traffic or handle it somehow differently, if you don't, if you do have good integration and don't just fly blindly, then all of a sudden you have much more airspace available for UAM. Okay, so that's one thing. The other thing is that, of course, we don't have to reserve the full height of the airspace for UAM. After all, they have some vertical precision, and if they can measure the height and stay on the height with a precision of 100 meters, plus or minus 100 meters, then, well, we can look at the available airspace in 200-meter bands. And here it is, again, the same maps the expected number of conflicts with aircraft at different pixels in the Stockholm area. And this is the one from the ground to 200 meters. And I will be showing a few others, and you will see how it changes. So here is 200 to 400, and so on and so forth. And you can almost see how the aircraft are flying out or into the airports. So I'll go again through them, make it like a little movie. So this is close to the ground, higher, even higher, even higher, even higher, and so on. So, well, you can see that different parts of airspace are available for UAM at different heights, because at different heights, you have different parts of airspace occupied by conventional aviation. Okay, so that was the occupancy. And now the risk maps, again, as before, we have the same hospital somewhere in Stockholm, and deciding where you can fly from it with UAM, depending on which height you are. So you can fly anywhere here, but you don't really want to fly anywhere here, or you probably cannot even fly here because you would have to intersect this area, which is super risky. So even if you are very close to the bottom here, if it's not zero, then it's still prohibitively high expected fatality rate. And again, I will flip through a few slides. So this is from 0 to 200 meters, extra 200 meters, more, and so on. So again, flipping back and forward on these slides, you can see how the available airspace changes depending on the altitude at which you are flying. And sometimes it's, well, kind of gives you the corridors, right? If you want to fly in this direction, then you should use certain height, and well, in this direction too. If you want to fly in a different direction, then you should use another height. Here you have some openings. So we didn't think about designing flight corridors yet, but this is something that LFV and others are, well, trying to do. I mean, one of the ways to manage the UTM traffic is to define the flight corridors for them, and pictures like this show you where these corridors should be. I will again flip through them back and forth before going further. So certain parts of the airspace are available. Of course, this 200 meters of performance requirement was a somewhat arbitrary thing, and it's interesting to look also at different thickness bands. And now we'll flip through similar pictures, but for 100 meters bands. So again, we start from 0 to 100 meters, and this is where the aircraft fly 100 to 200, and so on and so forth. And again, you can see how they're kind of flying farther and farther away from the airports, at giving you different kinds of available airspace at different altitudes. So that's the occupancy, that's where the aircraft fly. And then again, the mission risk map, still the same idea, flying out of this star, of this hospital, where you can and where you cannot fly. And wherever you see blue or red, you cannot fly. Whatever is clear, you can. And again, just flipping through, you can see how the available airspace changes with height. So gives you some ideas of where the corridors could be located. And 2 more slides just to show the comparison. Of course, we understand where these occupancy and risk maps come from. So here you have the risk map for for 0 to 200 meters, and it consists of the, well, occupancy between 0 and 100 meters plus occupancy between 100 and 200 meters. And you can see which 100 meters are better to use for flying. And similarly for the expected fatality rate. Again, so here on top you have the mission risk map for the full thickness band from 0 to 200 meters, and these are the first 100 meters and the second 100 meters. And well, I mean, one possibility is that you can say you really have to fly lower than 100 meters because there is much more available airspace than between 100 and 200 meters. But that may be too quick a conclusion. you need to do more holistic risk assessment, of course, taking into account the ground risk and many other factors. And there is actually a holistic methodology from Eurocontrol called Medusa for risk assessment, but we don't go into it. I will just mention it again, maybe in the last set of slides. And here I'll finish by saying, well, this air risk gives you one piece of the puzzle, but the puzzle in general is much more complicated, but still, this piece is also needed.